Welcome, everyone. Today, we are going to discuss a common hurdle for engineering teams as they scale, the 100-plus service problem. This post from the Kubernetes community perfectly summarizes the dilemma. The organization has reached a point where they have over 100 repositories, each deploying to Kubernetes using plain YAML. As they transition to Helm, they are questioning the best path forward. Is it better to have a Helm folder in every repository, or is there a way to create a single, abstracted chart that all applications can share? This is the central question for any growing organization. How do you manage Kubernetes deployments at scale without creating unmanageable complexity? In this session, we will look at how to move past this bottleneck and build a deployment architecture that truly scales. The first instinct for many teams when managing microservices is to create a separate Helm chart for every individual service. On the surface, this approach seems logical because it is simple to start and provides high isolation. However, this strategy quickly reveals its flaws as the environment scales. As noted in the testimonial, having dozens of services with copy-pasted charts turns routine tasks like upgrading ingressors into a miserable manual process. This leads to a situation where someone must go through every single chart just to ensure consistency. While the initial simplicity is attractive, the long-term reality involves massive code duplication, inconsistent standards, and error-prone updates. Ultimately, what starts as an easy way to get moving becomes impossible to maintain at scale. The overcorrection involves moving to the opposite extreme, the creation of a monolithic universal chart. This is a single, massive chart designed to handle every possible service configuration through highly complex conditional logic. As highlighted in the featured quote, while this approach aims for efficiency, it becomes incredibly complex in the long run. Eventually, it becomes so difficult to maintain that team members become afraid to modify it for fear of breaking dependent systems. Looking at the trade-offs, there are certainly benefits. This model maximizes code reuse by adhering to the dry, or don't repeat yourself principle, and effectively enforces a single standard across the organization. However, the cons often outweigh these gains. Such a chart becomes a single point of failure and is cognitively overwhelming for developers to navigate. Any change carries a high risk of an unintended blast radius, potentially impacting numerous services simultaneously. Ultimately, because of its complexity, it requires deep Helm expertise to modify, which creates significant bottlenecks for the engineering team. To achieve a truly scalable and maintainable deployment process, we should separate the logic of how we deploy from the configuration of what we deploy. As this diagram illustrates, the how, which includes deployment logic, templates, and best practices, is centralized in a library chart managed by the DevOps team. Meanwhile, the what, the specific application values, is decentralized and managed by developers in their respective application charts. The application chart then consumes the logic provided by the library chart. This architecture is made possible through Helm library charts, a chart type specifically designed for creating reusable and shared code across the organization. Let's examine what exactly a library chart is within the Helm ecosystem. A library chart is a specialized type of Helm chart designed to define chart primitives or reusable definitions that can be shared across other charts. Crucially, it is not meant for standalone deployment. There are three key characteristics that define a library chart. First, think of it as a building block. It contains only reusable templates, such as standardized configurations for a deployment, service, or ingress, allowing for consistency across multiple projects. Second, it is fundamentally not deployable. If you attempt to install a library chart directly, Helm will recognize its type and refuse the installation. Third, this behavior is explicitly declared in the chart.yaml file. As shown in the code snippet on the right, the type field must be set to library. This metadata tells Helm that the chart is a collection of helper templates rather than an application ready for deployment. By using library charts, teams can centralize logic, reduce code duplication, and enforce infrastructure standards across their Kubernetes environments. Looking at the anatomy of a library chart, the first critical component is the chart.yaml file, where the chart type must be explicitly set to library. This metadata tells Helm that the chart is a collection of shared logic and templates rather than a standalone application deployment. Within the templates directory, notice the specific naming convention used for files like _deployment.tpl and _service.tpl.
It is crucial to understand that the leading underscore is mandatory. In a library chart, Helm will ignore any files in the templates folder that do not start with an underscore. This requirement ensures that the library chart does not inadvertently attempt to render resources on its own. Inside these files, we define reusable snippets of YAML using named templates. By wrapping blocks of code with the define and end keywords, you create modular components that can be easily consumed by other charts. This structure allows you to maintain a consistent and dry code base across your entire infrastructure.
To consume a library chart, an application chart must first declare it as a dependency within its chart.yaml file. As shown in the example code, we define a regular application chart and include a dependency section. Here, we specify the name of the library, in this case, company-based service, along with the required version and the repository URL, which can be an OCI registry or a local file path. Before you can package or deploy the application, you must run the command helm dependency update. This step is essential because it downloads the library chart and places it into the charts directory of your application. The workflow is straightforward. First, define the dependency in chart.yaml. Second, run the update command to download the library, and once that is complete, your application chart is ready to be deployed. This transition from boilerplate to a single line represents the ultimate goal of our approach. On the left, under the old way, you see a standard Kubernetes deployment file. It is verbose and contains significant amounts of repetitive configuration for things like resource limits, liveness probes, and security contexts. Managing this across dozens of microservices is error-prone and creates massive technical debt. On the right, the library way shows the drastic simplification possible with Helm library charts. By calling a centralized template, we reduce the entire deployment file to just one line. All the underlying logic is inherited from the library chart, allowing developers to focus strictly on providing their application-specific values while maintaining organizational standards. The DevOps/developer contract establishes a clear division of labor and ownership within our infrastructure. On the left side of the contract, the DevOps team is responsible for the library chart, which acts as our base service template. Their focus is defining exactly how we deploy. This includes building the underlying Kubernetes object structures for deployments and services, enforcing company-wide best practices for security and probes, and managing networking and ingress logic. Conversely, on the right side, the development team owns the application chart for their specific services. Their responsibility is defining what we deploy. Through the values.yaml file, developers manage application-specific configurations, including image tags, replica counts, and environment variables. This structure ensures that while deployment mechanics are centralized and standardized by DevOps, developers maintain the necessary control over their application-specific behavior and scale. Enforcing a strict contract through the use of required values is a hallmark of a robust Helm chart. It ensures that the consuming application provides all necessary inputs, rather than relying on silent defaults or error-prone optionality. In this template example, we use the Helm required function to mandate specific fields. For instance, the replica count and image details are wrapped in a required call, accompanied by a descriptive arrow string. If a developer fails to define these values in their values.yaml file, Helm will halt the templating process and surface the exact error message provided. This proactive validation mechanism prevents broken configurations from being deployed to the cluster, significantly improving the reliability of the deployment pipeline. This diagram illustrates a common pattern in CI/CD pipelines, showcasing the separation of concerns between shared library charts and application-specific deployments. At the top, we have the library chart CI process, which is managed by DevOps. When a change is committed to the library chart repository, it triggers a sequence of steps: Helm lint for syntax checking, Helm test for validation, Helm package to create the distribution file, and Helm push to store the chart in an OCI registry. This ensures that shared infrastructure logic is tested and versioned independently. In the bottom section, we see the application chart CI/CD pipeline, managed by developers. Triggered by an application code commit, this pipeline first performs an AZ-ACR login to authenticate. It then executes a Helm dependency update, which pulls the required library charts from the OCI registry. Next, the pipeline builds and pushes the application's Docker image.
The process concludes with Helm upgrade-install, which deploys the application to a Kubernetes cluster. This architecture promotes reusability and standardization across multiple applications while maintaining a streamlined deployment workflow. The payoff of this approach is the achievement of truly scalable, consistent, and maintainable deployments. This is built on 3 key pillars. First, we have reusability, adhering to the DRY principle, don't repeat yourself. By defining common logic once, it is inherited everywhere, which effectively eliminates the risks associated with manual copy-paste errors. Next is consistency and governance. This framework allows us to enforce organizational best practices for critical areas like security, logging, and labeling across every service. Crucially, it empowers our developers to deploy correctly without needing to become deep Kubernetes experts themselves. Finally, we achieve maintainability at scale. A single change in the library can be seamlessly rolled out to hundreds of services. To illustrate this, consider a use case where the security department requires a new annotation for a service mesh. With a library chart, you simply update one template and bump the chart version. Every subsequent service deployment then automatically inherits that change. It truly feels like magic. Moving from chaos to order in infrastructure management requires addressing 2 common pitfalls. On the upper left, we see duplication and inconsistency, where individual charts for every service lead to maintenance overhead and configuration drift. Conversely, on the upper right, complexity and fragility arise from a monolithic universal chart that becomes difficult to update without impacting the entire ecosystem. The library pattern solves these issues by centralizing common logic into a versioned library chart stored in an OCI registry. This architecture allows app A, B, and C to leverage a single source of truth for their deployment logic while maintaining distributed configuration. Each application only needs to manage its specific parameters via a values.yaml file. This approach ensures consistency across services, simplifies updates through versioning, and provides the scalability needed for modern cloud-native environments. Adopting the library pattern begins with defining your standards. By creating a library chart, you encapsulate your organization's deployment best practices into what we call a golden path. This provides a clear, standardized framework for every team to follow, ensuring consistency across the board. Once the standards are set, we must establish a clear contract that separates responsibilities. In this model, DevOps owns the how, the underlying logic inside the library, while developers own the what, the specific values for their workloads. Utilizing required functions allows you to programmatically enforce this contract, maintaining system integrity. Furthermore, it is vital to treat your library as a formal artifact. You should version, package, and publish your library chart to a trusted registry. Recognizing it as a critical piece of shared infrastructure ensures it receives the same level of care, security, and governance as your primary production services. Ultimately, this approach is about scaling people, not boilerplate. By reducing cognitive load and eliminating redundant configuration, the library pattern allows your teams to grow efficiently, focusing their energy on innovation rather than repetitive manual tasks.